Hi all, in this video we're going to talk about linear regression. Okay? Linear regression, which is sort of the last part of this chapter, and it's a big part because it's describing uh, two variables together, but it's doing a little bit more than what we talked about previously. So when two quantitative variables again have a linear relationship, not some other relationship, we can do more than just report the correlation. Okay? We can actually create a model that describes the relationship between the two variables. And with that model, we can say and do much more. So when I have a linear relationship, what I need to do is I need to create a model, and that model is a line, okay? A literal line that you learned about in, I don't know, 6th grade, 5th grade, 7th, 8th, somewhere before high school. Okay? And so I have the line, basically y equals a plus bx. Okay, y equals a plus bx. Now there's a caret upside down, or not upside down, but there's a caret above the y, and you read that as y hat. Okay, y has a hat over it, and there's a special reason that y has a hat over it, and that reason is because it's being estimated. Whenever I'm in statistics and I'm going to estimate stuff based on data, okay, uh, I put a hat over it. So I have a plus bx, okay, where a is the y-intercept and b is the slope. Okay? Now you can change that around if you rather think of it as ax plus b, that's fine. Okay? I just put it a plus bx. There's no really rhyme or reason there. Okay? The regression line, that y hat equals a plus bx, is also called a prediction equation because I can use this line to predict the values of y based on some known value of x. So for instance, if I was, for some reason, really interested between the relationship of height and weight for college-aged males, okay? And so I really wanted to be able to say, if you give me the weight of a person, I'm going to then predict the height of that person. So hopefully that makes sense. Okay, then so I have some data on some people. I create a model, that line that describes that relationship between the two variables. And what I can do with that line is I bring in somebody new into the class or into wherever. They give me their weight, okay, but they're behind some screen, so I can't actually see their height. Okay, so nothing there gives away their height, but they give me their weight. Okay, and then I use this line to predict their height. Okay? If the line describes the relationship very well, then that's actually a really powerful tool. Okay, predicting new stuff is also very important in statistics, okay, and in general. Okay? If I'm going to predict whether or not a new ad is going to be a hit or a flop for my ad agency, okay, and for some reason, based on a bunch of different factors, there's a linear relationship between them, and I can use this line to sort of try to predict whether or not the ad is going to be a flop or not, then that really does something for my company. Okay? I know that was a contrived example, but hopefully it made a little bit of sense. So, for example, here is a plot, okay, of data that has a linear relationship. It's the relationship between a city and highway miles per gallon, okay, which hopefully does have some sort of linear relationship. And so I can fit, does it look linear? Yes. Okay, so I can fit a line to it, and I can describe that line. Okay, so there's the line, y hat equals 1.337x plus 0.892. So we got the line. What does that line tell us? What does that line tell us? And so in fact, what I'm interested in here is how do I interpret the slope and the y-intercept of this prediction line? Okay, and so this will take you back to interpreting the slope and y-intercept of a regular line. So, but these are, again, we're in the statistics world, and so they're going to be slightly different, and it's important, the difference is important. They're going to be slightly different than what you are used to. So, the slope is the average change in y for a 1 unit change in x. Okay, so if I increase city highway miles per gallon, okay, I expect, or the average change in highway miles per gallon is going to be 1.337. Okay, so that should make sense. City is generally lower than highway. Okay, and so as I increase a highway miles per gallon by 1, on average, I should see an increase of 1.337. The difference between this and a regular line with no backstory is that it's not an average change in y for a 1 unit change in x. It is the change in y for a 1 unit change in x. So that word average is the only thing that's added in there, but it's really important because it's acknowledging that cars are different. Okay, so this is not trying to predict for all cars. This is trying to actually predict for the average car. Okay, I understand that there are some hybrids out there that are going to get really good city miles per gallon, and then their highway isn't going to increase quite as much. Okay, or I could have some engines that are really bad when you sit. They aren't made for sitting in traffic a lot. They're made for going, high revolutions, so on and so forth. And so those are going to have not so. Their difference is going to be bigger. This is about the average, not about specifics. That's something that you have to think about to get your head around, but it's really different from what you're used to probably. The y. So here's an example, and here's what for this line what it means. For an increase of 1 city MPG, okay, we expect a 1.337 increase in highway MPG. Oh, great. The y-intercept is again not the value of y when x is 0, it's the average value of y when x is 0. So for this example, it would say for a car that gets 0 city miles per gallon, we expect the car to get around 0.892 highway miles per gallon. And if you think about this for a second, you should say, wow, that doesn't make any sense at all. And you're right, it doesn't. The value of the slope, or the interpretation of the slope, always has meaning in the problem, but the interpretation for the y-intercept may not have any meaning. Okay, certainly it doesn't here. The only way that it's going to have meaning is if values of 0 are actually in the data set, if they have some, if they make sense for the data set. So certainly 0 doesn't make sense in this data set because if you don't have any miles per gallon in the city, you basically have a car that doesn't have the engine in it. Okay, that's the only physical explanation for that, which doesn't make sense. So interpretation of the y-intercept may not have meaning in the problem. For slope it does, intercept not always. And so if I ask you a question like this, which I most certainly will, okay, you should be able to tell me the interpretation if it has meaning, and if it doesn't have meaning, then you should say it doesn't make sense to interpret the y-intercept in this situation. Okay, so now let's talk about linear regression. Okay, we made the line. So I made the line, I gave you the equation. Now I want to talk about how to actually make the line. How do we find the line of best fit? So you've probably actually done this before, okay, but you may not have called it linear regression. It's often called finding the line of best fit. Okay, so I have these points here. Okay, I have a couple points, and I want to, it looks like they have a linear relationship, so I want to fit a line. How do we do that? Well, it's kind of an interesting question because I can draw an infinite number of lines that go through the data. Uh, some are good and some are not so good. So here's a visualization. So with that same data, I drew 5 lines there. Okay, some are good, some are not so good. Okay, so you may look and you may see, well, the orange line doesn't fit the data at all. It goes through one point. But it's a vertical line, and we know there's not a vertical relationship between x and y. Okay. The blue line is not so good because it's actually depicting a negative relationship, that as x increases, then y decreases, which we see from the data doesn't make sense at all. Okay. The same sort of thing happens with the green line. It shows that as x increases, y doesn't do anything. It stays the same. And certainly that doesn't seem to be the case. And so we come down to purple and red, okay, which seem to be actually maybe decent descriptors of this relationship. The red line looks like it fits some points very well, okay, but it's kind of off. Okay, it looks like it's increasing too fast as compared to the actual data. And then, of course, I included the line of best fit, okay, which is the purple. But what makes purple so good? Certainly, I can look at it and I could give you those descriptors like I just did. Blue has the wrong pattern. It's not vertical. It's not horizontal. But how can I say that in terms like with numbers and metrics, mathematically, not just using words? So, can I choose a best one? Certainly, visually we can. How do we do that? Sort of not visually. To do that, I need to define something called a residual. A residual is the vertical difference between the actual point and then the predicted point for a particular x value. So at x equals 37, where I am there, okay, I have the predicted value, which is the line at that point, okay, where the line crosses a vertical line at the specific x value. And I have the actual point, okay, if there was, we need actual data to do this, so there are actual points, and I look at the vertical difference between the two. So that's a residual. And so to find the best line, I want the line that minimizes the sum of squared residuals. Okay, so the residual is y minus y hat. I want to square them and then add them all together. And so if we were in class, I would ask, why would I want to square them? Why do I need to square them? And the answer would be that I have some residuals which are negative and some residuals that may be positive. And so if I don't square them, then I could have some like cancellation. I could have a really bad line that has some really strong, really positive residuals and really negative residuals. When I add them together, they're going to cancel out. And so a line that's actually really bad could look good if I don't square them. When I square them, it turns all the negatives to positives, and it keeps the scale differences. So a small difference is still going to be smaller than a large difference, even though I square both of the numbers. Okay, so it keeps scale, is what I'm trying to say. There are formulas to find the slope and y-intercept of that least squares regression line. So the b and the a that I talked about before, okay, we can find them. There are simple formulas to find them. And so for the slope, b, I can find that by doing this simple formula, although really it's not so simple. It's the correlation coefficient r times s of y divided by s of x. So we have the formula for r in a few slides before. If I multiply that by s of y over s of x, then I get the value for the slope. Okay? And then the y-intercept is y hat minus the value of the slope times x bar. Sorry, not hat. Y bar, mean of the y values, minus the slope times x bar, mean of the x values. Okay? In practice, we'll always use software to find this line. I will never ask you to actually go through and do all these calculations by hand. So that's how we actually find the line, okay, is using least squares. So oftentimes it's called least squares regression. Now, I want to move on to another question, and that is, great, I fit the line, and I can talk about the line, but did it actually do a good job? Was it worth my while to fit this line to try and describe the relationship between x and y? Okay, so I can go through all of that I did before. With software, it takes like approximately a second to do. But was it worth that second? Did it actually gain me anything? Well, that's a big question, and there are ways that we can assess whether or not it was sort of worthwhile to do. And the way that we're going to assess it, one way, the way that we'll talk about here, is called r squared. Okay? R squared. We made the line, but was it useful? In other words, and so this is maybe another rephrasing that's a little better, did using a line to describe the relationship between x and y gain us any predictive power? Like, can I predict the values of y better now that I'm using this line versus just guessing? Okay, so if I go back to my example and I say, I want to find the relationship between the weight and height of college-aged males, okay, and so I fit the line, and so I get this equation that claims to increase my predictive power. I could do that, or if I didn't believe that there was any relationship between weight and height, I could just say, well, I know that on average, college-aged males are 5 feet 10 inches tall. Okay, so that's like the average height of a college male. Maybe, I don't know if that's true or not. I made it up, but we'll just believe that's true. So when that new person walks in, should I just guess 5'10", because that's the mean of all heights of college-aged males? Or should I ask them what's their weight, okay, and then use the relationship? If there actually is a relationship, that's going to make my predictions better than just guessing the average height of people, okay? But if it isn't much better, then why do I do it? Why don't I just use the mean of y? So I can measure how much it helped. And I measure that by something called r squared. It's called the coefficient of determination. So r squared is the coefficient of determination. It's interpreted as the percent of variation in y that can be explained by the linear relationship between x and y. Again, it gets back to the in other words that I talked about above. So, for instance, if I were looking for, never mind, actually, this is a slide that talks about sort of a different interpretation of r squared. It can also be sort of interpreted as the percent of variation that goes down based on the relationship between x and y. Okay, so certainly we know that uh, there are a lot of different heights out there. You can be very short or very tall when you're in college. Okay, and so here it's city versus highway MPG again. Okay, and if I looked at just the variation in highway, okay, variation in highway versus, so that's before I fit the linear regression versus what's like left over after I do uh, the regression. Okay, so it's not going to predict it perfectly. There are still some like variation points left over. For instance, in this city versus highway, uh, there are other things that I could take into account that may cause the differences uh, in highway MPG, not just the city mile per gallon number, but also maybe like what type the car is. Is it a muscle car? Excuse me. Is it a hybrid? So on and so forth. Excuse me. Uh, so differences in types of cars may also cause some of the variation in the response. And so R squared tells us how much was accounted for by our line that we made. So I know that was a lot, and I sneezed a lot in the middle. But if we look at the standard deviation of highway just by itself is 5.95, and then if we look at the variation in the residuals, it's 1.75. It's a lot smaller. If they were the same or very similar, then I know that the regression didn't really do anything to help me. Okay? That's all that I'm trying to say in this slide. So properties of R squared, it is literally the square of the correlation coefficient. Okay? It is literally R squared. Okay? So R went from negative 1 to 1. So if I square a number between negative 1 and 1, what am I going to get? Something between 0 and 1. So R squared is between 0 and 1. 0 happens when there's no association between the two variables, and 1 happens when there's perfect association. Okay, so great. So that's R squared. Now, there are some cautions in regression. So what should you not do? Extrapolation is extremely dangerous. What extrapolation is, I'll go back. What extrapolation is or does is when you try to predict values that are outside of the range of your x's. Okay, so back to our city versus highway mile per gallon example. Okay, if I predicted something with 30 city miles per gallon and got, I don't know, 40 highway miles per gallon, that makes sense. But it wouldn't make sense to say for a car that got 1,500 city miles per gallon, I'm going to expect that the car gets 5,000 highway miles per gallon. Okay? So the x that I used to predict was way outside of the range of x's that were used in the data. That's called extrapolation, and it's really dangerous because we don't know what the relationship looks like outside of the range of values that we always saw. Same with weight and height. A person can only get so tall and can only weigh so much before their body breaks down. So I can't predict someone who weighs sort of 1,000 pounds. Okay, you only get so tall. So certainly a person can get to 1,000 pounds. Okay? They may not pass away first, but they're likely not going to get any taller. So the relationship would actually look probably more logarithmic if I went out to the sort of like far reaches of possible values of weight. Outliers really affect the regression line. So before in chapter 2 we talked about resistance measures. whether something is affected by outliers or not. The regression line is not a resistance measure. Okay? It is really affected by outliers. So, for example, here is some points, and there's one outlier. We all see what the general trend is, but here's the example without the outlier. Okay, so the line goes exactly where we thought we would, but with the outlier, it's really pulled down towards that outlier. Okay, and the last thing that I want to talk about and spend some time on, although I know this video is long and I'm sorry for that, is the argument that correlation does not imply causation. Okay? And so this is something that, for instance, the tobacco companies really harped on for a long time to try to keep their business up of cigarettes, is that two things can be correlated, smoking and lung cancer, but smoking does not cause lung cancer. You can get lung cancer without smoking. So that's a correlation does not imply causation. There can be an association without one causing the other. Causal relationships can only occur when all other possible variables, okay, have been accounted for. So if there's absolutely nothing else that could be causing these differences, then that's a causal relationship. It's really hard to get a good causal relationship. You have to be really careful and make a really good experiment to try to look at causal relationships. So here's a quick example, and then we'll be done. Education, percent who completed high school in a city, maybe, and then the crime rate. So clearly there looks like there's a positive relationship between education and crime rate, but if I add in a third variable called urbanization, and I looked at them all together, as you say, like they're more educated, hence more crime rate is what you see on the left. But if you look at how urbanized a city is, then you see the relationship that you would have thought before, which are negative relationships. Okay, so that's correlation does not imply causation, and this last example here is what's called a lurking variable. It really changes how the relationship happens if you don't account for it. Okay, so that's the end of chapter 3.